Good morning.
Let's take a couple minutes to talk about the lab. And if there are any questions on that, I posted a video of me going through it without looking at it for a year. So it was like I was looking at it for the first time. Probably not the most efficient way to do it, but I guess it shows how I thought through the problems. And again, there's lots of ways to do these questions. So if you came up with a different solution than I did, that's fine too. So what did you think about the lab? Let me start with Morgan.
I felt like I was a little bit behind in the R part of that. So
That's okay.
Yeah, that took me the longest. That was what took me the longest on that one. Was just figuring out like how to tell R what I wanted it to do.
Right. So you had a conceptual map of what you wanted to do, and it was just figuring out how to get that done. I think that's a good skill to practice in this class, just in general, because that's something that isn't going to go away, right? That's something that a skill that you'll need. So just, I guess, think of this class as an opportunity to practice that. And it will get easier too. Some of the stuff we're doing now is kind of the stepping stones for the routines that we'll need to do when we actually get into modeling, like for loops and looking at choosing estimators, that type of thing. So they're built in there as preparation for the next steps too. So that's good. Good to hear the challenges with R. Anybody else?
Yeah, other than like what I mentioned last class, I feel like the counter variable for that fourth layer of the last problem matrix, like for whatever reason, I just really struggled with setting that up at first. So yeah, definitely had to ask around for help on that. But I will be really excited to see the solution. I would say I only feel about like 85% confident in my ability to recreate that work though. So I'm happy to like keep practicing this one.
Yeah, and to be totally honest, when I went through and looked at it again, I think I took an approach that was different than when I first wrote it. In that I just used I used an if statement instead of a counter. So multiple ways to do that. If you want to go over that counter, I don't think it's in the solutions, but we could talk about that too, maybe after class today. I don't think the lecture will take the entire time period, which I don't want it to because 2 hours is a lot of lecture material. Okay. Any other comments on the lab?
Did anybody talk about making matrices yet?
No, we haven't.
Well, it really showed me how lacking my skills are in conceptually picturing what I want the matrix to look like and pull out in my data frame later on. So excited to get better at that.
Yeah, and there was one place where I think I used a three-dimensional matrix too in the solutions. And that was, I had to look up how to do that exactly. Or I wasn't totally sure and I figured it out by looking at help menus. But do you want to go through a couple examples of making matrices?
I mean, I'd say yes, but I don't, yeah.
Yeah, let's just do a couple because it's, once you have the map on in your head, then it's almost always the same. So we could just do a couple examples here. Okay, so most common matrix that we have is, well, the most common command we use is matrix. And then the first argument, there's usually 3 arguments. The first argument is what you're going to put into that matrix. So if I want to create a matrix that has 1 to 4 in it, these are going to be what's going in the cell. So 1, 2, 3, 4 are going to go in those cells. Now I have to decide what the dimensions of the matrix are, and rows always come first and columns come second. So if I want a 2 by 2 matrix, so 2 rows, 2 columns, this is going to create a matrix that has 2 rows, 2 columns, and it's going to fill in those values 1 to 4, and it's going to fill them in by column. So it's column major matrix. So there's the matrix. It says 1, 2, 3, 4. If I wanted to create just a 4 by 1 matrix, so when I say 4 by 1, this is in all linear algebra and all matrices, the number of rows come first. So if I want a 4 by 1 matrix, 4 rows, 1 column, then I say 4 by 1 here, and that gives me a 4 by 1 matrix. What I often do beforehand is build an empty matrix. I'll just say NA here, create the matrix I want. Say I want a 4 by 4 matrix. Then I have an empty matrix that has all NAs, and I could store this as something like A equals. And then now I can put stuff into A. And the way I put stuff into A is by telling which column and which row I want to put into it. So if I want to put something, say, put a 3 right in the second row and second column here, I'm going to say second row, second column of A equals 3. And then I have this 3 right here. So that's how I can build matrices, by putting things in there. I can also say I want 3 in all of the second column of A, and that'll fill in the entire column. So we'll be doing that on subsetting columns where we want to put a value for the entire column in there. And I could do the same thing with the rows. If I want the second row of A, I can do that. So we can build matrices this way. Now, if I was building a for loop, let's try. This will address the counter issue too a little bit. Easy example of the counter issue. Let's make a for loop. First, I'll create this empty matrix A here, and let's say I want to fill this individually by row and then by column. So let's make a nested for loop. So this is part of the lab here. So let's say for row I in 1 to 4. And then outside of that, we'll do the columns for J in 1 to 4. I can clean this up by doing Control I again. Now let's say we'll call this counter equals 1. And then we're going to say A in the ith row and the jth column is going to equal our counter. Then after we put that in there, we're going to say counter equals counter plus 1. Clean this up a bit. So what am I doing here? I'm starting off a for loop. I'm going to start I and j equal to 1. And then I'm going to cycle all the way through 4 for each one of these. So it's going to set I equal to 1. It's going to go down. It's going to run all the commands within the braces, go back to the top, and then I is going to be set to 2. And it's going to run all the commands and so on until it gets to 4. And once it gets to 4, it's going to go to the upper loop, and then j is going to equal 2, and it's going to start over on the inner loop. And every time we do that, we're going to say counter. Let's see, actually, one quick correction. Okay. We're going to start counter at 1. So this is going to be a 1 when it first gets in here. But then as soon as it puts that counter equal to 1 in this spot, it's going to overwrite itself and say counter equals counter plus 1. So then it's going to equal 2. So next time it goes up to the loop, counter is going to equal 2, and it's going to keep going through. So counter is just going to keep getting bigger and bigger and should eventually equal 16 because we have 16 iterations to do, 4 times 4. So let's look at this. Then look at our matrix A. Does that make sense how that works? Does that help with the counter a little bit, Kelly? That's the idea of what that was. So when we were talking about going through 1 to 50, you could say when counter equals 1 to 50, don't do anything, but as counter gets greater than 50, then start saving these values. Okay, what do you think, Mia? Is that helpful?
Yeah, thanks. Appreciate it.
All right, let's go to our lecture notes. So today we're going to be talking about any questions about the lecture material from before we start. Let's see, what did we talk? We talked about a lot. Oh, deterministic models is the last part. I had a discussion with some other people in NRES yesterday, and we're talking about developing a set of courses that would result in a quantitative type background in the department for PhD students or master's students. And one of those courses that we felt was kind of currently lacking. I mean, it was just a discussion of 3 of us, so there may be other things out there. Maybe Angela knows some other courses out there too, but one of the courses we kind of felt was not being taught was a theoretical ecology course, or kind of like a calculus for ecology, where we think about all these deterministic models and how to create those models for looking at theory. So that's something that might be offered in the future, and would really, instead of one lecture on deterministic models, it'd be a whole course on developing models for to describing ecological processes. So if that does come to fruition, that will be taught by Bob Shriver, because he's interested in that, and that would be that would give some more background into some of the things we're going to do here when we incorporate those theoretical models into a statistical framework. All right, so that's what we talked about last time, deterministic models. Now we're talking about rules of probability. So these you may have seen in an introductory stats course. Yeah, so let's just get started. So here's what we're going to be talking about for the next few lectures. I don't know if it'll be 3 or 2, but there are quite a few topics here, and this is what Lab 2 is about. It concerns these topics. So the first thing we're going to be talking about is the rules of probability that support Bayes' theorem. This is our principle-based approach in getting at what Bayes' theorem is and why it works, why it does what it does. Conditional probability in the law of total probability. That's it. 2 rules that completely describe Bayesian analysis and why it works. There are some other useful use we'll talk about today. We'll talk about independence, the probability of disjoint events, probability of alternative events, and the chain rule of probability. Kind of like the chain rule of calculus, but much easier. Factoring joint probabilities using the chain rule. This becomes important when we just break up models into data models, process models, and prior models or parameter models. Factoring using Bayesian networks. So who's heard of Bayesian networks? Okay, interesting. You hear a lot of people talking about Bayesian networks, Bayes nets, but all they are is these directed acyclic graphs of a way of writing out hierarchical models. So again, another buzzword that's just another hierarchical model. There's a theme there. Probability distributions, we'll talk more about that. Marginal distributions, this is what we use for inference when we're writing manuscripts. And then moment matching is a really useful tool that we can use to incorporate prior information into our analysis. All right, so these are what we're going to be talking about. Why are these important? Well, here's a key of why each one of these things becomes important. So on the left, we have the concept that we're going to be talking about, and then on the right, why we need to understand this concept. Conditional probability is the foundation for Bayes' theorem. This is the probability of A given B. And in Bayes' law, we have the probability of our parameters given our data. So that's a conditional probability. The law of total probability is the basis for the denominator in Bayes' theorem. So we'll be talking about that probably next lecture. And the denominator in Bayes' theorem is the least well understood, or probably the most complex part of the equation. Independence. Independence allows us to simplify fully factored joint distributions. Factoring is the procedure for building hierarchical models, how we break things up into data models, process models, and prior models. Chain rule probability is how we do that. Probability distributions are the toolbox for our Bayesian approach. So we're always going to specify probability distributions or parametric models for unknown quantities. Moments, you know about moments, but maybe you haven't heard of them specified as moments. A moment is, for the normal distribution, the first moment is the mean. The second moment is the variance. There are additional moments too that we talk about less frequently. I think the third moment is skewness or asymmetry. And then the fourth moment would be kurtosis. And the moments are what allow us to summarize the posterior distributions of our parameters given our data. Marginal distributions are Bayesian inference is based on marginal distributions of unobserved quantities. In the background, there's some complex multidimensional distribution, some cloud of points, but we want to summarize those, marginalize over those to look at one parameter at a time. And the moment matching, I mentioned this already, allows us to embed deterministic models into any probability distribution, also allows us to use prior information. Okay, so why the rules of probability? This goes back to what we were saying in the lecture of what set Bayes apart. Bayesian inference treats all unobserved quantities as random variables. This is what was profound about Bayesian inference. The rules of probability are the laws that govern those random quantities. So we can think of the rules of probability as the algebra of the random variables. There's only a few of them, so it makes things easy. So this turns out to be pretty useful because it allows us to use the rules of probability to build and interpret Bayesian models. This is not true for other branches of statistics. This is why when we're interpreting 95% credible intervals, it's so easy because we can use the rules of probability to do that instead of some other concepts based on hypothetical repeated observations. Okay, so what is a random variable? A random variable is a quantity whose values are governed by chance. All right, what does this mean? Well, let's look at something that might be a little more familiar. Early on, I asked if people had seen the function about the R norm function. So let's go to RStudio. All right, we have a random variable A. R norm, which most people said they had some familiarity with, is a way of generating values randomly from a normal distribution. And we get to specify the mean and the standard deviation. The mean and the standard deviation, it's the first and second moment of the normal distribution. And a fact about the normal distribution is you can completely specify the normal distribution by describing only the mean and the variance. There are other distributions that require more parameters to specify it. Things like negative binomial distributions requires more parameters to describe what that distribution looks like. But with a normal distribution, we can completely specify it with the mean and the variance. Now, here's a random variable A. The value of A when I execute this command is governed by the probability distribution of the normal distribution. Probability distribution of the normal. Okay, so when I do this the first time, I get 0.8008875, right? But if I do it again, I get something different. This is what's meant by governed by chance. There's a function in the background that's going to tell you the overall outcome of what A will be in the long run, but for each one, they're slightly different, and there's chance that's governed by chance is described by the probability distribution. And we wrote out what the probability distribution of normal was in one of our lectures. It was, I'll write that out again. So with the normal distribution, we have the probability that, let's say, A equals any value of A given the mean and the standard deviation equals 1 over the square root of 2 pi sigma squared times e to the negative 1 over 2 sigma squared. And then I ran out of room. A, since we're talking about A in this example, minus mu squared. So this is a mathematical function that looks something like this, where this is our value mu, and A can occur anywhere in here, but it's described by this shape, which the shape is determined by this function. Where we have higher values, we're going to have more likely values of our random variable, and where we have lower values on this curve, those values are going to be less likely. So if we look at, if we say, instead of sampling one value, we sample 100, it should resemble this curve described by this function. We can look at all those values of A. That doesn't do us too much good. So let's just look at a histogram of A. And we see we have it centered, the histogram on 0, and then the spread is described by sigma squared. Okay. And so this is what we talked about. Random variable is a quantity whose values are governed by chance. In our example with our R script, A was our random variable. Governed by chance means these values arise from a probability distribution. We talked about the normal distribution and what that function looks like. Bayesian inference treats all unobserved quantities as random variables. So missing data, predictions into the future, predictions across space, anything that we don't know is treated as a random variable. We seek to understand those distributions, and that's what our objective is with Bayesian inference. Now, in terms of notation, this tilde here, you'll see this a lot. This tilde represents what we were just showing with that R normal distribution, meaning there's some probability distribution that's going to describe the outcome of our random variables. So let me talk a little bit about notation here on the whiteboard. So in our example in R, we had A, and this is our R script. A equaled R norm. We had N equals, let's say 1. And then we had mean equaled 0 and standard deviation equaled 1. All right, so that's our R script. So how would we write this out statistically? Well, this is where we use this tilde notation. So if we were writing this out mathematically or statistically, we would say A tilde normal with mean equal to 0 and variance equal to 1, or standard deviation equal to 1. If we had a lot of observations, so when I first showed the R script, I had just one sample. Let me go back there. Say explicitly what I'm talking about. If we had just one example, it might look like what we just wrote out. So we have one value that comes from a normal distribution with mean 0, standard deviation or variance equal to 1. But if I change this to 100, then I'm going to need to modify this slightly. I will say A, the ith value of A comes from a normal distribution. Again, with mean 0 and standard deviation equal to 1. And then I would say for I equals 1 to 100 to indicate that there's more than one value that's coming from that normal distribution. But that those are all going to be centered on mean 0 and have a spread with standard deviation equal to 1. Okay, so this is notation. Going back and forth from statistical models to R script becomes really useful, especially when you're reading other people's work. You're trying to recreate it, taking that work that you read someone else does. They have a good idea that you want to try, taking their mathematical model and bringing it over into R to see exactly what they've done. All right, any questions about that tilde? In the R script, we still use equals instead of tilde for the most part, when because we're assigning an object. Although when you're using linear models, you see that. So if you have the R script, LM, Y, they use a tilde here given X for a linear model. So that tilde does show up in some R script, in some predefined packages. And that's to align with the statistical model here. So that tilde just means it's not deterministic. It's being generated from a random distribution. And then when we use equals, that's usually represents a deterministic relationship. So tilde describes a random variable. Equals means it's going to be exactly equal to, there's no uncertainty associated with it at all. So let me write out a model that uses both of those as an example. And this will be our logistic regression model. First, I'll write out the R script. It would be something like GLM Y tilde X family equals binomial. And then you may say something in here like link equals logit. I don't know the exact syntax for that, but it's something along those lines. And I think you may not even need to define this because the logit link might be the default choice. All right, so that's the R script. We're trying to, Y's are ones and zeros. So if we had our Excel table, we had Y's and X's. Y's would be ones and zeros. Let's say the presence or absence of a rare species, a rare flower across the landscape. You went and searched plots, 100 by 100 meter plots for the presence or absence of the species you're interested in. If you saw it, it got a 1. If you didn't see it, you got a 0. And we're interested in how that relates to the amount of moisture at that site. So X would be the moisture, Y would be the presence or absence of the species. And say moisture is on a scale between 0 and 100. So if we had 75 here, 25, 80, 20, and we're trying to make inference about the relationship between the presence of the species and the amount of moisture in the plot. So that's the background for this model here. How do we write this out? Well, here's going back to our point from the lecture slides that we can use both equals and tilde in a single example. We have Y. We're going to assume Y comes from a binomial Bernoulli distribution. It has some probability of success mu. And we think mu, the probability of success, is deterministically linked to the amount of moisture. We might say the logit of mu. And I need to put an I on here because we have lots of observations. We don't have just one. Equals beta 0 plus beta 1 times xi. So here we have an equal sign. If we know x, we know beta 1, and we know beta 0, we know exactly what mu is. It's just a deterministic relationship, what we talked about last lecture. But when we know mu, we don't necessarily know what y is going to be. This is that uncertainty, or a random variable. Y is a random variable before we collect the data, governed by chance. And it's going to be centered around some expected value mu, but we won't know exactly what y is going to be before we collect the data. All right, any questions about this notation, the tilde and the equal sign? To me, I think it's useful to think about how these things are generated in R. Is everybody okay with this, or should I take this example and plug it in R? Okay, I'll move on then if everybody's okay with this. All right, so that's on notation. An event is a specific outcome of an experiment or survey, a specific value of the random variable. So we can show that in R easily if we say, let's set the seed. Setting the seed in R will it'll keep track of the randomness so that we can recreate the randomness if we need to. So let's say we're interested in one event, and we're going to call that 2021. We're going to collect data this year. That's going to be our event. So if I set the seed and sample from R norm, this is event A. The value of A is negative 0.12246. That was the specific event for the seed equal to 2021. And once that event occurs, that's fixed. It's no longer random. So once we observe it, we observe the event. That's what our event is. So if we go out, before we actually collect the data are random. But then when we go and collect the data, that's the event that occurs, and that's no longer random. All right. All right, concept of probability. The concept of probability A, or the probability of A equals the probability that event A occurs. And what we need to know A is to know what all the events could have been described by our sample space, and then what proportion of that event is described by A. So if this is event A, to figure out what the probability of A is, we have to divide the area of A by the area of our sample space, or the support of our random variable. All right, conditional probability. This is what we use for inference in the Bayesian setting. Conditional probability is the probability that event A occurs given that we know B occurred. So if we know that B occurred, we know that if we're throwing a dart at this board and someone told us the dart landed in B, so we know the dart landed somewhere here, and then they ask us, okay, given that you know that it landed somewhere in here, what's the probability that it also landed in A? So we can see that only place that could have occurred is at this intersection here. But we can also rule out all of this area here. By knowing that B occurred, we can rule out this entire area here. So we know a lot more about where it was likely to occur. We narrowed our window down, our area of probability down from the entire space S down to here. And we can narrow it even further by knowing that, or trying to figure out where the probability of A is. So we know it's, okay, we know it's occurred somewhere in here. What proportion of this space is also in A? All right, so using this, if we know the probability of A given B equals the area of A intersecting with B divided by the area of B, we can calculate what this is. Up on the top right, we have what's called the joint probability. The probability of, let's see, the area of A intersecting with B. So the joint probability is this intersection here, probability of A and B. So if we know what this is, we can divide that by the probability of B to figure out what the probability of A given B is. So let's take this equation and then ask, how would we rewrite this to say, what's the probability of B given A? So take a minute to write that out, and then we'll look at that. Okay, Meredith, what do you think?
So it should be the same on the top and then P probability of A on the bottom.
Right, yeah. Follow-up question. Is probability of B given A equal to probability of A given B?
No.
Okay. Another follow-up question, but I'll ask someone else. When would the probability of A given B equal the probability of B given A? Let's see, I can only see the top 5 is Bryant, are you there? Okay.
If A and B were the same size.
Exactly, right. Okay, so let me I changed the notation slightly to align with what we'll also see in this course. We talked about notation early in that these types of notation shown on the slides and then the square bracket notation mean the same thing. This shortens things up a bit when we start writing, when we start factoring distributions, it's nice to get rid of those P's in there. All right, so the first case was on top here where the probability of A given B, probability of A given B equals the joint distribution of A and B divided by B. So that goes on the bottom. And then when we ask what is the probability of B given A, we just replace this on the bottom here. Now, if A equals B, probability of A equals B, this is what Brian was saying, if they're the same size, then they're equal. So then this equals this. Okay. We did this one. We did this one. Is probability of A given B equal to B given A only in certain cases where they're equal, where the probability of A equals the probability of B. All right. So conditional probability. We talked about, this is essentially what we defined. The equation that we used last time, the last couple slides, here is the definition of conditional probability. Probability of A given B equals the probability of A and B and divided by the probability of B. So that's our definition of conditional probability. We're going to make use of this, of rearranging this equation. So we can always break this down, the joint distribution down into the conditional distribution times the marginal distribution. So this is the joint distribution when we have a comma in there. Then we have the, so joint distribution, then we have the conditional distribution of A given B, and we often refer to this as the marginal distribution of B. The way the rules of probability allow us to factor this. So there's theory behind this. We could prove this worked. That's what you would do in a graduate level statistics course, showed that this was true. We can just take it for granted that this equation holds. So we're going to be making use of this to factor out joint distributions into a combination of conditional distributions and marginal distributions. Okay. We often talk about correlation in ecology when two things are likely to occur together, and we talk about independence. Independence, statistically, the statistical definition is that when we know that B occurred, it provides no information about the probability of A. And to writing that out mathematically looks like this. The probability of A given B is exactly equal to the probability of A. So knowing this B here tells us nothing about A. And we can flip these around too. If we know that A occurred, it tells us no information that B occurred. Let's see, I have some R script to show this too, but okay, let's go to R script just quickly. What does that look like in R code? The random variable A, we can generate 100 values for our random variable A. We can generate another 100 values for random variable B. So these are two independent random variables. When we plot them, it looks like this. Knowing where we are on the A axis doesn't tell us much about what the value of B is. So what does dependence look like? Well, let's generate an independent random variable A. And then for B, let's say the mean equals A. And we plot those and we see that if we know something about A, it's going to tell us something about B. So if we know where A is on this x-axis, it's going to tell us something about where B is, about the relationship. So in this case, if we know A is large, we know that B is going to be more likely to be large. And if we know A is small, we know B is more likely to be small. So those are dependent events. And here we have independent events. And we can see that B is dependent on A because it's in the function. It shows up in the mean. We could take this a step further and say, well, let's fit a model to see if there's a relationship, if A and B are independent. So let's say we'll fit a linear model. Does B depend on A? And we can look at the summary of that model. Oh, I didn't rerun this. And we see there's a statistically significant relationship for the slope of A. 0.8924 is the slope describing the relationship between A and B. We can also look at the correlation or covariance of A and B, and we see it's about 75% covariance. So it seems like they're not independent, right? What if we do, let's see if this will work. Yeah, I would have to. See A given B, same thing. Yeah, we still see that correlation. Doesn't matter which one's on the x-axis or which one's on the y-axis. But if we did this one here and did the same thing, we don't see a significant relationship between the slope in A and B. And if we look at the covariance between the two, much smaller. All right, so in terms of the Venn diagrams we've been using, what this means is that the area of A intersecting with the area of B divided by the area of B is exactly the same as the area of A divided by the sample space. Okay. So here's an exercise to look at factoring joint distributions. Use the definition of independence shown here in equation 1 and the definition of conditional probability that we looked at first here to show that the joint distribution of A and B equals the probability of A times the probability of B when A and B are independent. So let's take a couple minutes to go through that derivation or try that derivation, then we'll go through it. Okay, anyone want to take a stab at this? Need some more time? Okay.
I can try it.
Yeah, go ahead, Meredith.
Okay, so you just take the first equation for the definition of conditional probability, and because you know that A and B are independent, you can just replace the term on the left with P of A, and then you can just multiply times P of both sides times P of B, and you get what's on the bottom.
Yeah. Yep, that's right. And I did it a slightly different order, but they're both right. I'll show what I had here. So the question is, does A, the joint distribution of A and B equal A times B? So I use a slightly different notation here again, just to link the two, when A and B are independent. So we start off with the definition of conditional probability, which is what Meredith said, where I did the multiplication first. So I got the joint distribution by itself first by multiplying by A. And then from there, we could say independence implies that B given A equals B. So then we can replace this with this B. And then we have the joint distribution of A and B equals a probability of A times the probability of B when A and B are independent. Okay, so if A and B are disjoint events, if they don't have zero overlap, we call this mutually exclusive, means you can't be in both A and B. Then the knowledge that that event B has occurred means that we know that A has not occurred. And when that happens, the joint distribution or the conditional distribution of A given B equals 0. So if you know B occurred, there's no probability that you'll be in A. This becomes useful with things like if an animal lived or died. If it lived, there's zero probability that it died. And we can rule out certain cases. And we'll see some of those models later on. All right, the probability of A or B. So or is described by this union symbol. And it means what's the probability of being either in here or in here. And the equation to calculate that is the probability of A plus the probability of B minus the intersection of A and B, or minus the joint distribution of A and B. So why do we subtract this here?
We subtract, sorry.
Go ahead, Morgan.
Okay, sorry. We subtract the intersection because we're looking at the probability of one event or the other. So if it's in both of them, then it doesn't mean it was just in one.
Anybody want to follow up on that?
Yeah, I guess we don't necessarily care here whether it's A or B. So we just want the total area in this case.
Okay, so we want the total area, and then why would we subtract off that A and B if we want the total area?
I think because it would count it twice because you have both probabilities.
Right. That's the reason. So we have, if you add up all this area here, and you add up all this area here, you're counting up this area twice. So we only want one of those. We want the total area of this shape here. And by counting up all of A and all of B, we're counting this little section twice. So we want to subtract off one of those sections. And one of those sections is described by the probability of A and B. So there's still an area A and B in here. We still are interested in this area here, but we're only, just to do the surface area, to get the surface area correct, we want to subtract off one of those. Law of total probability. This is important for the denominator and Bayes theorem. It's the most confusing one to look at and try and conceptualize. But if we have three disjoint events, B1, B2, and B3, and then we have some proportion of A that falls within those three events, we can calculate the probability of A by summing up the probability of A in this area and multiplying it by the probability of B, and then adding it to the area and A in this area and multiplying it by the probability of B, and so on, for as many different areas as we have. So to calculate the area of A, we first have to figure out what the area of A given B1 is, then the area of A given B2, and then the area of A given B3. And then we have to kind of weight it by how much probability B1, B2, and B3 has. So in many ways, it's like a weighted sum. We're weighting A by how much area B1, B2, and B3 has. So this first part here, the probability of A given Bn, where n represents 1, 2, or 3, and then we're going to add them all together, would be, if we're talking about n equals 1, is this area. So this is the probability of A given B1. So we take this area and then we multiply it by the probability of B1. And we do that for all of our different sections, and that's going to tell us what the probability of A is. If you look up Bayes' theorem, this is in the denominator on the right-hand side. You either see this whole thing here, or you just see the probability of A. So let me just write that out. So in terms of our parameters, what we're interested in for Bayes' theorem, we have probability of theta given our data y equals likelihood of y given theta times theta divided by, you either see it written like this for shorthand, or this n here is the sum sign. So we sum up all the different values of n from n equals 1 to 3 in this case. Yeah. So this equals this. So this is where this total law of probability shows up in our Bayes theorem. Now, this is often very hard to calculate. And why MCMC, Markov chain Monte Carlo algorithms, the genius behind those and why they're so useful is because it allows us to cancel out this denominator here. Before MCMC was around, before 1990, we could only do Bayesian inference when we could actually calculate this bottom quantity. And that's difficult for most problems. But the genius of MCMC is it allows us to get rid of this bottom term, and replace this equal sign with a proportional to sign. So we'll get into that in much more details. That's just a precursor of what's coming. So this is what we end up using. And it obviates the need for us to calculate this, which can be very difficult to calculate for real world problems. All right, integral sign. Every time an integral appears on a PowerPoint slide, an angel dies somewhere. So what is this integral? Integral, essentially, this is why I said dust off your, in the last lecture, your calculus book and look at the definition of an indefinite integral. Integral here just means we're making the sum of these areas really small. So we have lots of tiny little smalls. It's going from a discrete area to a continuous area. So as these areas, these points, they become more and more of them, and they get smaller and smaller. We replace the sum with the integral sign here. And so a lot of times in Bayes' theorem, you see this in the denominator instead of that sum sign. So just as an example, let's look at definition of a indefinite integral or a Riemann sum. When we're integrating, we try and figure out the area under this curve. And we could do this coarsely by saying, all right, let's make some blocks. And then now we have lots of blocks with lengths and widths. And so we can figure out what the height of this is and the width of this is and calculate that. H1 times W1 plus H2 times W2 and so on. Add up all the areas of the blocks, right? And that looks like for I equals 1 to n, the height of block I times the width of block I. And that'll give us a rough approximation of what the area under that curve is. But if we want to get a better and better approximation, we make the width of those smaller so that we have less of this, these areas and less of these areas where it's not actually on the line. So if we make the width very small, let's say as W goes to 0, the limit of W goes to 0, that gives us a much better approximation of the area under that curve. And all we're doing with that integral sign is all we're doing with that integral sign here is replacing this notation with a integral. So that's how we go from this equation to this equation down here at the bottom, from this to this. So a lot of times in Bayes' theorem, you see this in the denominator. All right, let's see. Let's, how many slides do I just have a few slides left. We can, anybody need a break? Okay, good to go. We can generalize this factoring of joint distributions. And in fact, we can generalize it indefinitely for as long as we want. So we can break up, we started off by breaking up, I think I have some audio issues here. Can you hear me okay? Okay. We can, maybe I just got a little too loud and I started hearing feedback. We started off by breaking out this joint distribution. Now we're saying Z, but before we had A, B, and so on. Now we're going to say, well, we have actually many more different random variables we're interested in. Z1 all the way to Zn, and Zn can be big. And we just broke up the probability of A and B into the probability of A given B. Well, if we have lots of different random variables in our joint distribution, which we will have for Bayesian models, we can break this up into the probability of Zn given everything else multiplied by the probability of Zn minus 1 given everything else times the probability of Zn minus 2 given everything else. Keep going down the line until we get the probability of Z3 given Z2 and Z1 times the probability of Z2 given Z1, and finally times the probability of Z1. So we can break up this huge joint distribution into we can factor it into all these conditional distributions. And these rules, this chain rule of probability is what allows us to break our models into hierarchical models consisting of data models, process models, and parameter models here. So there's a pattern here. When we build models, we choose a sequence that makes sense. And this was Berliner in 1996 was the one who first described these data model, process model, and parameter model, which is just using this chain rule of probability to factor a very complicated joint distribution into conditional distributions that make sense. So let me go through an example here. We'll start off simple with, I'll write out a model for simple linear regression. Oops. So we are interested in the joint distribution of mu and sigma squared given y. I'll put an equals here. So this is the joint distribution here. I'm going to start simpler. This adds a little too complexity too quickly. Let's start out with A, B, and C. This equals A given B and C multiplied by B given C multiplied by C. And we can keep going with this. A, B, C, D. We can do the same thing. A given B, C, and D multiplied by B given C and D multiplied by C given D multiplied by D. So it's like a telescoping process. That's where the name chain rule comes from, because it's very similar to chain rule in calculus as this telescoping effect. So this becomes really important for factoring joint distributions. So let me now add a little complexity to this and actually talk about a model and a posterior distribution and use Bayes' rule. So I'll go back to the example I started with, where I have yi comes from a normal distribution with mean mu and variance sigma squared. So we are interested in, we haven't gotten to this yet, but here's a foreshadowing of what's to come. We're interested in the posterior distribution of mu and sigma squared given our data. We can factor this into y given mu and sigma squared times mu times sigma squared. This is multiplied by here and here. And when we were talking about Bayes' rule earlier, we said theta given y is proportional to y given theta times theta. It's exactly what we see here, except thetas consists of mu and sigma squared. So theta equals mu and sigma squared. All right, let's do our hierarchical model for the first time. This is a linear mixed, it's called, if you've taken a mixed effects, a course where you've done any type of mixed effects models in the likelihood framework, this would be called linear mixed effects models, where the model looks like yi comes from a normal distribution. With mean mu and variance sigma squared. And mu comes from a normal distribution with mean beta 0 plus beta 1x and variance sigma squared mu. You could also write this, you may have also seen this written as yi equals beta 0 plus beta 1 xi plus ei. Well, let's see. And then maybe plus eta I. Or one other way, I talked about 3 different ways of writing the same model. Yi comes from a normal distribution with mean mu and variance sigma squared. Mu equals beta 0 plus beta 1 xi plus ei. This is probably the most common way you've seen this. And then ei is normal. You hear about fixed effects, random effects, that type of thing in the frequentist world. In this case, our fixed effects are beta 0, beta 1, and then ei is a random effect that has some mean and spread. Okay, so I will take this to the next page. And we can write out the model for this and see how we can, the goal here is just to see how we can factor these joint distributions. So our parameters of this model are beta 0, beta 1, sigma squared y, and sigma squared epsilon, given our data. I'm getting a little bit ahead here. So if this is not comfortable yet, that's okay. We're going to talk about this in much more detail. I just wanted to, I'm going to use this example we'll talk about later as a way of looking at how we can factor these joint distributions. So this is going to equal y given beta 0, beta 1, sigma squared y, sigma squared epsilon. I'm going to use this let's see. I'm going to use mu instead of beta 0 and beta 1. So y given mu and sigma squared. So we have this first part, y given mu and sigma squared. And then mu is going to depend on beta 0, beta 1, and sigma squared epsilon. And then we have sigma squared, this sigma squared, beta 0, beta 1, and sigma squared epsilon. So the take-home point of this is we can break up this complicated joint distribution of our unknown parameters, given our data, into these different levels, where we have this y given our parameters, and then we have this chain rule here where we have mu on the right-hand side and mu on the left-hand side. And then we break mu into the parameters that make up mu here. And then we have these individual distributions. So let's think about this in terms of a hierarchical model. The definition of a hierarchical model is that one of our unknown parameters, in this case mu, occurs on both the right side and the left side of this conditioning line. When you have that, that's the definition of a hierarchical model. And we'll get into much more detail on that when we talk about factoring joint. And we have a lot of practice in the next lab on factoring joint distributions. Now, if we were writing this out for a manuscript after doing an analysis, and this was the model we would fit, we could describe this as the data model because it describes how our data is generated, y. This as our process model because the process we're interested in is this mu. That's describing the relationship between our data, our covariates x, and our data y. And then each one of these are considered our priors. So we have prior distributions on every one of our unknown parameters. So our data model, our process model, and these are our prior models. And remember, each one of these square bracket notation represents the probability of y given something. So these are all described by probability distributions. So this would be shorthand for the normal, which is 1 over square root of 2 pi sigma squared e to the so on. We talked about that earlier. This would be maybe something else. This is actually also a normal distribution. And then we have to choose distributions for each one of our priors. And we'll talk about how we choose distributions for those. And by doing all of this, we get the joint distribution of our unknown parameters given our data. And that's our goal for inference in Bayesian inference. And it's all because we can factor these joint distributions using this chain rule probability. This is the theory that allows us to do that with rigor. Okay. All right, diagramming joint and conditional distributions. These are what are called Bayesian networks, or directed acyclic graphs. We have some joint distribution of A and B. So A and B. We can break our joint distribution into the probability of A given B times the probability of B. And we can break it up in this way. And we have nodes on the top and bottom. A is a node, B is a node. Heads of arrows are called children. Tails of arrows are called parents. Yeah. So we can go, sometimes the reason we have these up here, sometimes it's useful for people to think in terms of these directed acyclic graphs. A lot of people find it useful to draw out how everything's connected in these DAGs. And then from there, they can describe what the joint distributions are, or vice versa. We can go from our joint distributions to our directed acyclic graphs. So I have a couple examples of that in the next 3 slides, and then you'll have in the next lab, there's going to be practice going from both of these going down and then going up. There are examples in the book as well on this, and I think some of the actual lab exercises come right from the book. So if you're interested in more description of how we do this, we can describe that. But all right, we have 3 parameters. So we are 2 parameters in this first one. So we start off with the probability of A and B, and then we just break this down into probability of A given B times probability of B. If B was on top here and A was on the bottom, we just reverse the order of these. We have the probability of B given A times the probability of A. And we can see how these factor out with examples. So let me just go through a couple examples. In terms of our rules, all nodes at the heads of arrows must be on the left-hand side of the conditioning symbol. But then those ones sometimes become at the bottom, and then they lead up to something. So if you have a chain of 3, that's, again, the definition of a hierarchical model where you have the bottom, the middle, and the top. So the ones that were on top become on the bottom, and they switch from the left to the right-hand side of this. So just let me go through a quick example here. If we start off with a joint distribution of A, B, and C. And we see this equals the probability of A given B and C, the probability of B given C, and then the probability of C. So we factor it just like we did before, but now we see there's this logical order here where we have A conditional on B and C, B conditional on C, and then C by itself. So again, we see B on both the left and right hand side of this model of the up and down line, and it's a hierarchical model. And we typically say this is a data model. This is our process model. And these are our prior models. Or this is our prior model.
Hey, Barry, real quick, that notation on the bottom looks identical to on the previous slide, where there's an arrow from B to A and then an arrow from C to B and also C straight to A.
Yeah. So, okay.
Is there a difference in how you might write that?
Okay, so you're saying if there's not an arrow here, is it different?
Correct, yeah.
Right, okay. Let me see, probability of A given B and C. Yeah, okay, so this, right, that's a correction. I made a mistake. So if I was going to, so the way it's written now is correct, but the way I had it before, thank you for pointing that out, would be A, B, and C. Is that different? A given B, B given C, C. Yeah, I think that's the correct way to do that there.
Cool, thank you.
Yeah, and we see that in this example here. Let me switch to the slides. We see A doesn't have D and E connecting to it, so we just have probability of A given C, the probability of B given C, and then the probability of C given D and E, then each of the prior parameters for D and E. Here's an example where Bayesian analysis and factoring things like this is really useful. At the top of these DAGs, in our examples, let's say here, A usually represents our data. Things at the top usually represent our data, and then the parameters feed into our data. And we're trying to estimate what the parameters are. In many analyses, we have multiple data sources. So one example that I see in population ecology is that we will collect data on both information on survival, let's say a waterfowl species, on how it survives by collecting mark resite data. But we'll also have counts, abundance counts. So someone will go out and not only see which animals they can find with neck bands, that's our mark resite data, that gives us survival information, but then they'll count the entire population too. So we have two data sources. We have mark resite data, which will give us information on survival, and we have information on how many animals are actually out there. So these are two separate data streams. They're not independent because survival is going to affect how many animals there are. And one of the beauties of hierarchical modeling is we can incorporate two data sources into our analysis. So if you have two lines of information on the same process that you're interested in, you can incorporate them both by factoring them in this way. So in this case, A and B represent two different data sources, and C is the process that's given rise to each of these data sources. And in many cases, the two different data sources can tell us information that we don't actually have data on. And if we put them together like this, like we have in this model, we can learn about C in ways we wouldn't have been able to other ways. So for example, going back to my example with waterfowl and counting the number of animals and estimating survival, if we have data on how many animals there actually are, and we also have data on how animals survived from one year to the next, there's a missing piece in there, because if we go to our basic ecological model of population dynamics, which is our BIDE model, the number of animals equal the number that were born minus the number that died plus how many animals were there last year. If we know the number that were there last year, the number that are there this year, and how many died from our survival estimates, we can fill in missing information on how many were actually born, even though we didn't even look at how many were born. So we can combine these two different lines of evidence and make inference on these processes we wouldn't otherwise have been able to. So it starts to open the door for data we might be interested in collecting. If we can collect pieces of data here that can help fill in the picture to processes that we would not otherwise be able to gather information on, it opens the door. Okay, and then this last slide is generalizing. We can generalize this for as many ends as we want. Okay. All right, so that's my last slide. It concludes our lecture on rules of probability. These become the foundation for what we're going to be doing in the future. Any questions?
Harry, can I ask a question on the last slide?
On this one that's showing right now?
No, on the prior one.
Okay, all right, good.
Yeah. I had to point you to the right spot on the probability of C given D E.
Mm-hmm.
I see that in the DAG, but then why are you multiplying it by probability of D and probability of E?
Okay, yeah, so that goes, say that again.
I was just saying, why is that part of the
okay,
the model?
Yeah, that, let me go back a few slides here. So when we did, if we look at the very basic case where we have just A and B, we have the probability of A given B times the probability of B. So what it is, the analogy to our basic case here is it's this last component here at the end. So if I was to draw out this model, let's see. I have A on top and B on the bottom. So this is the probability of A and B. It equals probability of A given B. And then we have to include this part at the end, the bottom node at the end. So if we were to extend this, let's say, now we have the probability of A, B, and C. This is going to equal the probability of A given B and C. But we also have to include the bottom parts here. So we always have to include these bottom nodes at the end of our probability statement. So going back to that example you were talking about at the end, we have the probability of A given C, the probability of B given C, then we have probability of C given D and E, and then we just include those bottom ones, those bottom nodes at the end. Yeah, we have to include all of our nodes in here. And there's nothing that feeds into them, so they're by themselves. Does that answer your question?
Okay, I see. I see that. Yeah, that makes sense. Thank you.
Yeah, so if we were to extend this example a little bit, A, B, C. And then say F goes into D.
Perry, we're
G.
still on your slide.
Oh, all right. Okay. Thank you. So if we were to extend this a little bit and say F feeds into D and G feeds into E, now we have A, B, C, D, E, F, and G equals probability of A given C, probability of B given C, probability of C given D and E, and then we have probability of D given F, and the probability of E given G. And then we have to include those F and G at the end. To complete the specification of the model. And then what these are in the Bayesian sense at the end, at the very end of the line, or at the very start of the line, these are what become our priors. So our priors are going to feed into our process, and then our process feeds into our data.
Okay, that makes sense. I didn't know that they need to be included if they weren't part of the, I guess they're part of the chain. So they have to be in there.
Yeah.
So when you're drawing a network out like this, you always only have nodes for data, process, and priors.
Your process models, yeah, but you can have multiple data.
Yeah.
You can have multiple lines in your process too. So
But those are the three categories.
Right. That's the way that they were broken up that way in 1996, and people found that really useful to describe data and then the underlying process and then the priors. So those are typically the three general categories that describe the model. But within those, you can have lots of different processes going on, lots of different data sources. Yeah, but those are the three categories. Okay, any other questions, not only about this, but about lab?
Are we working with the same folks again for lab, or should we talk about
no,
that?
I haven't, did I post the lab yet? I may have posted the lab, but I haven't set a due date because we haven't talked about everything yet. We're starting to get into it now, but let me randomize the order. So, lab 2. Okay, so there is Morgan and James, Brian and Meredith, Kelly and Mia. And let's say 2 weeks from Monday is when it's due. So a week and a half from now. So we have a deadline. So the 15th, that's President's Day. I don't think we have that off. Monday the 15th.
I think that is a holiday.
Is it? Okay, that's interesting. All right, so then we'll do 2 weeks from today. And Angela, did you want to work independently or did you want to join a group?
I'm really behind on the homework, Perry.
Okay.
I might forever be behind on the homework, but
Okay.
this is I do have data sets that I'm working on, so
Okay.
for papers, so this is good.
Okay, sounds good. All right, anything else? If not, then have a good weekend and we'll see you on Monday.